Hello and welcome once again for another daily differential equations video. Today we'll be doing an annihilator approach example to solving differential equations. So the idea with the annihilator approach is we think of things in terms of as an operator. In this case it's going to be linear operators because we're solving linear differential equations here. So I'm going to rewrite this as though it's an operator form. And basically the complementary solution, which is, recall, for complementary, then the 9d squared minus 4 times y should be equal to 0. That's the complementary. And this is solved by, I'm going to solve it as, I'm going to replace the d squared here with an m, just so that we don't confuse the operator here with the solution. So it's solved by this, and we can see pretty easily that this becomes m squared equal to 4/9, which means that m is equal to plus or minus 2/3 if I take the square root of both sides here. So it's equal to plus or minus 2/3, which means that my complementary solution looks like c1 e to the 2/3 plus c2 e to the minus 2/3. However, the idea behind the annihilator approach is that we want to make this side, the right hand side, go to 0 using the operator approach, using an operator that makes this go to 0. Because if we're able to find an operator that does that, we can multiply that operator by the operator here, and it's obviously going to go to 0 when one or the other of those operators is 0. Then we're able to find the solution. So basically, the hard part of this is to find when an operator which will set this function to 0. So the question is, what operator makes sine of x go to 0? Well, what we can do is we can kind of experiment around with differentiating this. So let f of x equal to sine of x. Then we do know the following facts. F prime of x is equal to cosine of x. And that's not actually going to be too helpful with trying to eliminate sine of x, right? But what about f double prime of x? Negative sine of x. Now notice I have a sine of x and a negative sine of x, and there's an easy way to make that go to 0. It's by using f double prime of x plus f of x, which in operator form just says d squared plus 1. Okay, so d squared plus 1 will make sine of x go to 0, because if I do d squared plus 1 sine of x, right, that is equal to 0, which is what we were trying to do with the annihilator approach. So the annihilator approach, the idea is we want to make that function go to 0. Now, this will not work for all functions, but this will actually work for a larger class of functions than the traditional method of undetermined coefficients would. So this annihilator approach is a bit more powerful than the more straightforward method of the superposition approach to the method of undetermined coefficients. Okay, so now we know what the annihilator is, and so now the idea is basically this. We say d squared plus 1 times 9d squared minus 4 is going to be equal to 0 now, because I multiplied. Let's actually explicitly write this out first. D squared plus 1 times sine of x, right? But this goes to 0. So now we just have d squared times y, I should say. D squared plus 1, 9d squared minus 4 times y is equal to 0. And this will give us the complete solution, y. We already know what yc was, but notice that if I replace this with m squared, just to make sure that I don't mix up the operator here with that, if m squared, we already knew the solution for this. This was plus or minus 2/3. And this one gives me plus or minus I, right? M squared implies m squared equal to minus 1, which implies m is equal to plus or minus I, the square root of -1, right? So then what we're going to get for a solution is we're going to get c1 e to the 2/3 plus c2 e to the minus 2/3. And when we have a pure I here, it's obviously going to be e to the I and e to the minus I, but when we have that, when we have purely imaginary, then this is just really going to be plus the, say, c3 times the sine of x plus c4 times the cosine of x. That's what the solution is going to look like. And this is what we should expect at this point for linear differential equation, that if you have a forcing term, because that's really what this term on the end is, it's like a forcing term to the differential equation, that the solution is going to have terms that probably look like the forcing term. Okay. So now we would like to find C3 and C4, because notice that this is actually the complementary solution if I look at this. So this part then is the particular, which means we should be able to find C3 and C4. And the nice thing about this method, the annihilator method, is that we don't have to make a guess as to what the solution form should look like and then go back and revise our guess. This is just going to automatically give us our the form of the solution. So we just literally have to go back and find C3 and C4. So to find C3 and C4, we're going to recognize that this is the particular solution. So particular is going to be C3 sine of x plus C4 cosine of x. And that means that yp prime is going to be equal to C3 cosine of x plus, well, minus in this case, C4 sine of x, and yp double prime is going to be minus C3 sine of x minus C4 cosine of x. And just like we've done before with other method of undetermined coefficients, or in previous videos I've shown examples of this. Now we're going to say, well, 9 times yp double prime plus, minus 4 times yp is equal to sine of x. And now I can substitute in those terms, so I get minus 9 times c3 sine of x. And then this is going to be minus 4 times c3 sine of x. And then this is going to be minus 9 c4 cosine of x. And plus now minus 4 c4 cosine of x is equal to sine of x. Now notice that there's no mixing of terms here. It's just c4 only is assigned with cosine, and c3 is only assigned with sine. If there was a mix of terms, we couldn't we couldn't directly do this. We would have to say set c1 plus c4 equal to 0 or something like that, or whatnot. But in this case, there's no mixing here. There's only a c4 cosine and another c4 cosine, which means that c4 has to be 0, right? Because there's no cosine term on the right-hand side. So by examination, since there's no, I could write it out explicitly, right? I can minus 13 c4 cosine of x is equal to 0, which obviously implies c4 is equal to 0. And minus 13 c3 sine of x is equal to sine of x. And if I divide through by sine of x, that implies minus 13 c3 is equal to 1, which obviously implies c3 is equal to minus 1/13. And so now I can go back and finish up my solution. Y is going to be c1 e to the 2/3 plus c2 e to the minus 2/3 plus, actually minus because of the minus 1/13 there, minus 1/13 sine of x. And that will be my solution. Okay? Hope you enjoyed the content, and see you again soon.